we can sort of agree and disagree, and in a certain sense the tutorials are setting the standard for all the beer conversations that we're going to have throughout the rest of the week. What I want to talk about, of course, here is, oh yes, the original speaker for this tutorial was Kevin Ruth, but Emily, his wife, is very pregnant, and so that's why they needed a replacement, so some substitute here. Which is great, because then I can disagree with Kevin. He's not going to be here. Anyway, I'll be talking about the design of probability theory, and words here mean a whole lot. No word here is innocent. The meaning of probability, as we were here in the previous talk by Professor Tenti, is crucial. If you take a very good approach to probability theory, where probabilities are frequencies, and this is like really good. The whole of 19th century physics and the whole of 20th century physics is based on probabilities being frequencies. So this is like really good. But you may be stuck, and you may reach a dead end, and it may not allow you to proceed further. For example, if you take the wrong interpretation of probabilities as being frequencies, this definitely affects data analysis, right? You have to invent wacky fields like statistics in order to be able to do data analysis. But it also affects foundations of physics in a big way. If the only approach to probabilities you have is frequencies, then you're going to have to find in your problem a set of trials so that you can define the frequency. The set of trials may be an ensemble, as you do with statistical mechanics, or when you take the problem to quantum mechanics and things get really weird, you may have to invent many worlds. So there are the interpretations that you use for probability will really guide you as to what counts as a model for nature or a theory of physics. This is really important. So that's why it's so important to look for other possibilities. Now, one of the problems with frequencies is that, in principle, you're supposed to look for a number of possibilities, a number of successes in a very long number of trials, in principle, an infinity. Since you cannot reach that, then you may actually start changing words and saying things such as, this is the frequency that you would get if you could have an arbitrarily long set of trials. So you're starting to talk about possibilities, model interpretation. So this is an improvement of the frequentist approach, degree of possibility, the model interpretation, and there are versions of quantum mechanics that pursue this kind of approach. You could also think of probabilities as propensities or degrees of objective potentiality. This smells a lot like physics, doesn't it? The idea, many of these approaches were developed, are being developed, and they're reasonable things too, they're not. When you're desperate, you try things, okay? They are being developed to account for the problem of quantum mechanics. Another possibility is to discuss probabilities as degrees of personal belief. The degree to which you, and as an individual, may actually believe in something. Now, this is also a very promising approach. Names like Definetti and Ramsey and Savage are associated with it. I mean, it's actually a good way to proceed. I tend to think of this as being a little bit like too subjective, a little bit too wishy-washy. It's not quite what one needs if we want a community of physicists agreeing with each other as to what it is that things look like out there. So you might want to make it a little bit more, or rather, instead of emphasizing the subjective parts of these probabilities, how about if we try to account for the fact that we want to be a little bit more objective? You can believe whatever you want, but if you believe in the wrong thing, you're going to be objectively wrong. So we want to capture a little bit of that. So we may actually try to define probabilities as being degrees of rational belief, which which is nice until you start asking yourself the question, belief? Rational? What do these words mean? Degree of reasonable expectation. This is very reasonable. What does reasonable mean? Here's another one. Degrees of implication. I should start by saying that I actually like these, right? These seem to be, these last two at least, they seem to be like extensions of logic. We know what, well, we may not or not, but we have an idea of what it means to say A implies B. How about if A does not fully imply B? It's a degree of implication there. Now, I like all these three. They may seem at first sight a little bit different from each other, but if you ask the proponents of the laser thingy is very, very close to the change slides one, and so it's very easy to no one with Parkinson's should be pushing these things, so you'll get it all wrong. So I really like these three here, and if you ask the people who use these sort of words what they actually mean when they do this, when they do it, see how they act, how they behave when they use this sort of approach, what you will find is that they will behave in exactly the same way as these people here. So my trivial conclusion out of this is, look, the interpretation matters, but no single short phrase will do justice to the full complication of the subject. So we have to be very careful. For example, why do we care whether A implies B? Logic. Well, you care whether A implies B because if A happens to be true, then you will believe that B is true as well. So the reason you care about such an object here is precisely because it gives you guidance as to what it is you ought to believe, which is precisely what that is. So words are tricky here, but we have to use words. Very good. So let me continue here and say, well, the inspiration for all of this is the Cox approach for degrees of rational belief, or as he called them, the degrees of reasonable expectation. There. He started the whole approach. Oh, by the way, yes, and I should make a comment about something you said there, how he ended up publishing something that was completely original in the American Journal of Physics. It had to do with the fact that if you wanted to publish anything that had a bearing on philosophy or foundations, physicists were in those days, and to this day, now it's getting a little better, but if you wanted to publish anything that had a bearing on foundational issues, it was totally nuked in physics journals. So the only way you could actually publish in Foundations of Quantum Mechanics or Foundations of Probability Theory was by going to a pedagogical journal and saying, no, I'm not doing research, this is just pedagogical stuff. And so for the longest time, the good papers in Foundations of Quantum Mechanics were in the American Journal of Physics. Now it's changing, fortunately. Very good. So Cox based his approach on two axioms. One that refers to negation, and I'm assuming that you guys kind of know some of this stuff. Another on conjunction. This is the plausibility of not A given B. It's a function of the plausibility of A given B, and this is the plausibility of A and B given C. It's just some function of those two, and from this, remarkably, the laws of probability follow. I'm going to come back to that later. So I'm just setting the stage. But there are a number of objections that have been raised over the years to this kind of approach. I find the approach totally reasonable. I'm sold, right? But that's not enough. The fact that we here agree with each other, and we don't, let's face it, right? In order to get Bayesians to disagree with each other, you only need two. So let's not claim that we agree. We agree enough to be able to argue. We can communicate, but that's the way it is. Anyway, for example, what are real numbers? If you're trying to compare propositions, propositions be compared? You can compare them according to the strength of your belief, whether how much you believe it is true. You can compare to the extent to which you believe that you wish them to be true, the utility. You can compare them to the extent that, to which extent one leads you to, is relevant to figuring out whether the other is true, their relevance. You can even compare them as to the number of bits that it takes to communicate one or the other, right? So you can compare propositions in many, many, many ways. How do we know that a single real number will capture a probability? This is a serious question. We say, real numbers, proceed. I have a little bit to say about that, not too much. But are the axioms reasonable? Are they true? What on earth do you mean by true, right? That's another problem that is actually serious. I'm not going to touch much on that. But are the axioms reasonable? To me, they're extremely reasonable. To many of us, they are extremely reasonable and unavoidable. But to many other people, they aren't. This is still a small community. This is not 2,000 individuals. It's only 100. So why not, for example, an axiom that says the plausibility or the degree of rational belief in A and B given C is not just a function of those two, but a function of all the possible combinations. That's a possibility too, right? And so why should we say something as reasonable as this? If you want to figure out if A and B is true, you first figure out if A is true. If A is false, you're done, right? So you have to know whether A is true. The function should depend on this guy here. Having decided that A is true, then you will look at B. So it makes sense. But we're talking about something strange here, a theory of inductive inference for induction to figure out what happens when we don't know what's going on. Why not include all possibilities? Very good. So what I want to do, and that was by way of introduction, even what we think is given, what we think is easy, is not necessarily so obvious, and the proof is the rest of the world doesn't believe us yet. It's increasing, it's getting better, but there is more to be done there. So how do we come up with a theory of inductive logical inference? The goal is to develop tools for reasoning when we have incomplete information. We don't have enough information to make deductions. The approach that I'm going to follow here is extremely pragmatic. And I am using the word pragmatic in both a colloquial sense, we want things to work, and also in the very philosophical sense of pragmatism. The tool that we're going to develop, probability, is designed to achieve a certain purpose, to perform a certain function. So this is an engineering problem. We want to reason with incomplete information, we need tools. We're going to develop the tools. Now, if we need tools, we're going to have to be very, very explicit about the purpose that this engineering approach is supposed to perform, the purpose of the tool, and what are the design specifications that we're going to impose on this tool. So, how do we develop probabilities as degrees of belief? The crucial thing is that we are not concerned with the personal beliefs of particular individuals. If that is your problem, that's fine. You can go ahead and try to elicit their beliefs by seeing how they will react in gambling situations, and that's important, to figure out what people believe. It's a very important problem. That's not the problem that I'm tackling here. So that kind of extremely personalistic probability is a very legitimate solution to a different problem. What we want here is, or rather the problem we face, is not that I have these beliefs and I want someone to elicit my beliefs and figure out what my gambling behavior is. The problem is much more serious. I don't know what to believe. If you ask me about a particular problem, I have no idea. So forget it, I'm not going to gamble. I'm confused. I don't know what to believe. So what we need is we seek guidance. We need a strategy, rules, to figure out what we ought to believe. Kind of interesting, the word out there. It's not innocent at all. Is there a connection with ethics and how you should behave, how you should decide what's the right thing to believe, the wrong thing to believe? Yes, there is. So there are implications that are much broader than just competitive inference is as broad as it gets. There's nothing broader than that, but that's another question. So what we want a framework to do is build up a framework, design a framework that will tell us what we ought to believe if only we were ideally rational. Let me put it this way. So we have ideally rational agents here, not these poor people that are actually real. The problem that I have in mind is the following. Suppose you want to add numbers. And if I ask you guys, what's 2 plus 3? Or rather, is 2 plus 3 equals 5? 2 plus 3 equals 5. Is that true? You say, yes, of course. You didn't have to do arithmetic to do that. You just, you believe it. It's in your guts. Suppose now that I tell you A plus B equals C, and I give you numbers where A, B, and C are like 6-digit numbers or 7-digit numbers, monstrous numbers. And I ask you, okay, what do you believe? Is it true or not? What do you do? The bottom line is, you have no idea. You're confused. You don't know what to believe. So you say, well, you know what? I don't know. I know what happens when I deal with small numbers. Let me sort of come up with rules, and I'll extrapolate them, and playing that, the same rules are going to apply even when we're dealing with large numbers. So for example, there is a successor, n, you can figure out n plus 1. If you have the successor of the successor, n plus 1, that's the same as n plus 2. That kind of trivial rule that we invent just by looking at what we want to achieve from the small numbers to the big numbers, this is what is going to allow us to figure out if A plus B equals C works when you're dealing with huge numbers. So you're going to end at the end saying, I believe, or rather, I have checked that A plus B equals C. Equals A plus B equals C. For huge numbers, I have checked that it satisfies, it's in agreement with the piano axioms and all of that, and therefore I realize that I ought to believe it is true. Do you in your guts actually claim that you believe these complicated calculations are true except for the fact that you actually done it? No, you don't. So what we're doing here really is we're trying to figure out what we ought to believe. Whether you believe it or not, doesn't matter. And we are assuming that these individuals are ideally rational. So now the question is, what on earth do we mean by rationality? When are you considered a rational being? You can offend people really quickly here, okay? The standard approach is if you're using your brain, you're rational. I don't know. So what is rational for some individuals may not be for others, and so on. So this is a very, very tricky question, and you have to be very cautious. So what do we mean by rational? So here I'm going to give some guidelines. Okay, we call beliefs rational. This is going to be very minimal if they are appropriately constrained. What I want to capture here is that you can only say you're rational if anything goes. If you believe whatever comes your way, you're not being rational. Okay? So the fact that there are some rules constraining your beliefs, that's an important ingredient in rationality. That there must be some rules. The beliefs ought to, or the strength of your beliefs ought to obey appropriate rules. Now, what rules are you going to use? That's another difficult one, right? The method of divine revelation, for example, seems to be very acceptable for many individuals, but not for others. So what rules do you follow? It turns out that this is a very difficult problem. Of course, I can't give you an answer. What's rationality? But certain instances of irrationality are blatantly clear. Okay, so it's very difficult to define rationality, but irrationality sometimes is very easy to identify. Okay, it's a little bit like pornography. I can't tell you what it is, but you know it. You know it when you see it. Okay, same thing with rationality. There. How about that for a slogan? Rationality is just like pornography. There. If some blatant irrationalities are avoided, then you may be striving towards some rationality. Now, remarkably, this is almost enough. So the pragmatic approach will work as follows. The framework is meant to be useful, to work. It is not meant to be true. This is deep, right? If you want to build something, the goal is not to build something that's true. It's to build something that works. It's a completely different problem. So, but in order to be useful, the framework must do certain things. Like, for example, it is absolutely crucial that it be of universal applicability. This is difficult now. And there is a reason why. If we want to do a framework for handling incomplete information, the framework has to be of universal applicability. There is a reason for that. And the reason is you want to use this framework in situations where you don't know what's going on. So if you do not know what's going on, how are you going to pick between the various tools? You don't know enough about the problem. So what we're going for here is the bare foundations, the bare minimum that a method must have so that you can start working towards making an induction towards reasoning with incomplete information. Now, this requires thinking, okay? As promised, this is a tutorial where the purpose is to get you confused, not to say, oh yeah, it's so easy. It's not easy. These statements are not innocent. But they already say something here that is absolutely crucial. If you come up with a theory of probability, it's not going to make any sense. And the framework is not going to be useful if you're going to start having to say, well, you see, if I do the statistical mechanics of classical gases, or if I do the problems in which I'm flipping coins, I'm going to use classical probabilities. If I now tackle problems in quantum mechanics, then the rules change completely, and I'm going to have quantum probabilities. So this is important, all right? If I do economics, then I have to do economic probabilities. How about medical trials? Different set of probabilities there. How about engineering? Do you need to do fuzzy logic and all of those other things? Now, granted, many of these approaches can actually be useful in particular subfields. But if you want a theory of inference that's going to be useful when you don't know what's going on, you need something that's a little bit more general, more universal. So this is important. If I accept this, and I do, quantum probabilities are out of the picture. They must also allow quantitative reasoning, and I don't know why. Because it's useful, okay? Many of these, they're not supposed to be true. The framework is supposed to be useful, and quantitative reasoning is particularly useful to making predictions. So here we go. That's part of what the framework is supposed to accomplish. Now, how do we know that the framework is working? You ask your engineer, design or something, come up with a process here or a device that has to work. How do you know that it is working? And the engineer will come back to you and say, well, I know it's working because I designed it to do A, and it's doing A. I designed it to do B, and it's doing B. So we know that a framework is working, or we mean the framework works when it performs according to certain design specifications. Now, the design specifications reflect what we want to accomplish. They're not true. It's just what it is that this framework is supposed to be doing. They are guidance to what we want the theory to do, to accomplish. They are not axioms,
And in particular, they are not meant, these design specifications, not being axioms, they are not meant to describe some sort of hidden Platonic reality where these mathematical theories might have some sort of objective reality out there. None of that. This is a purely pragmatic approach to solving a very real human problem. What do we do when we don't know what's going on? Very good. So let's get quantitative here. What we want is a theory that will describe intensities of belief, the strength to which we are entitled to believe in something. Now, the point is here going to be that intensities are like any other intensities. They can be ranked in a transitive way. If you believe in A more than B and B more than C, then you believe in A more than C. And that is why degrees of rational belief are going to be represented by numbers. Not because it is the right thing to do, not because I have proved it to be this way, not because this is what probabilities are truly like. It's because I'm designing a framework that's supposed to do something like rank various propositions according to the intensity of the belief I should have about it. It's a matter of design. The notation that we're going to use is the standard one. Propositions of A given B are like that. The degree of rational belief is going to be initially written like this. We have negation, we have conjunctions, and we have disjunctions or. So this is the very standard approach. So now this is like the second part of the talk. The talk has one part that goes like 35 minutes, another part that goes like 30 minutes, and another part that goes like 30 minutes, right?
Not for this channel.
So this is now I'm gonna get a little bit more technical about how we implement this philosophy of designing probability theory as a tool for accomplishing goals. And I'm going to introduce a very nice pedagogical device here that I'm sure you'll recognize. Anyway, I'm sure you'll recognize. The design specifications. Here we go. The design specification number one is that the tool, if it's going to be useful at all, it should be used in situations where I don't know what's going on. Therefore, it should be universal. Degrees of rational belief are related to each other by rules that are of general applicability. This is like really important. It's only because these rules are general that the whole thing is going to work. For or, we're going to say that the degree of belief that A or B given C is a function of all the possibilities that you can come up with where the context C is kept fixed. Similarly, for and, the degree of rational belief of A given B in the context of C, I'm going to write all possibilities. So this is a little bit different from Cox. Not philosophically different. Well, it is philosophically different. I'm not extending logic. I'm being like an engineer trying to solve a practical problem. But the mathematics will end up being very, very similar. The second design specific. Oh, yes. I have to be a little bit careful here. F and G, these functions here, have to be reasonable to be useful, right? Have to be reasonable. By that, I mean, first, non-trivial. The functions f and g are not allowed to be constant, independent of their arguments, because that would mean that your degree of belief in propositions is going to be 0.73 no matter what. That's not what you want. So that the first thing is that these functions are supposed to be non-trivial. And also, we would like them to be continuous, differentiable, blah, 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 because if you change your degree of belief in one of these guys just by a little bit, and this guy changes by an incredible amount, you know that there is something engineering-wise that's not working properly. So those are technical assumptions that we're going to make there. The second thing is that you want to avoid blatant irrationality. We want our assignment of degrees of belief to be consistent. And what we mean by that is that if a particular degree of rational belief can be calculated in two different ways, the two ways must agree. So this is the standard Cox approach. So we look first at the sum rule. We look at, you see, we have a function there with 4 arguments. Functions that live in spaces of 4 arguments are like, these are big spaces, so it's big complicated. So let's simplify the stuff a little bit and look at the special case where the 2 propositions A and B are mutually exclusive. So then the function f gets reduced to just 2 arguments because 2 of these guys here happen to be just the degree of belief that something is completely false, completely unbelievable. Whatever that number is, we plug it there. So this is a function of just 2. And the consistency requirement follows from the associativity constraint, which says that if you have the degree of belief of A or B or C, this can be computed in 2 different ways. Either you do A or B first, or you do B and C, and then C, or you do A and then A, B, and C, B or C all together. Standard Cox. So we have 2 ways to compute the same thing, and if you push this, what you find is that the function f has to satisfy this associativity constraint, which is a functional equation, and you have to go ahead and solve it. And lots of this, lots of stuff has been written about this equation starting back in the 19th century. And so I'll just write the answer. That's a pedagogical device of great value. It's obviously shown that. It's easy. It follows, right? So this is my first instance of this. I just say general solution is this function of just 2 variables is going to be given by, there is a function phi. And so we have not just one function, we have a whole family of them. Depending on the function phi, we have different functions f. Phi is essentially anything you want, except that it has to be invertible. So that's kind of important. So being invertible, it's going to be monotonic. So, but this is the general solution. And so the interesting thing is that consistency requirement led to an incredible slew of possibilities as to what the function f is supposed to be. So conclusion, consistent degrees of rational belief are such that the degree of rational belief for A or B is going to be given by whatever the function is, something like that. So this is a possibility. Now, this is a kind of ugly and not very useful solution because we still do not know what phi is. But then this is what probably the place where Cox really nailed it. This is the genius at its most raw form. He realized that if you apply the function phi on both sides of the equation, then of course this one cancels out, you get it over there, and so you get the phi of this is the phi of that plus the phi of that. And given that this function phi is monotonic because it is invertible, we can always regraduate to a more convenient scale. So your scale of degrees of belief was initially correct, but inconvenient, not useful. So rescale your scale of degrees of belief in such a way that the new degree of belief, which I call here C, is the function phi applied on that. With the new rescaled degrees of belief, this is what the way you combine degrees of belief for mutually exclusive propositions to find the degree of belief for the conjunction. So the idea of regraduation is what I want to point attention here to. What this says is that you may have many different possibilities as to what a consistent scheme, a consistent framework for handling degrees of rational belief is. There are many. Each function phi will give you one. But essentially, they're equivalent. Because it just changes of scale will give you the same sum rule. So here, conclusion. Given any consistent assignment of degrees of rational belief, we can always regraduate so that OR is represented by a sum rule. Incidentally, this sum rule already implies that the degree of belief in A, given that not A is true, which is the degree of belief that something is actually, the degree of belief that you assign to something when you actually know it's false is 0. So the 0 comes from there. It's not something we have to postulate. Very good. We can prove this, and this is my proof. You don't have to read it. It exists. Remarkable. It exists and it can be put within one page. Yes, that's it. Okay, so this is my pedagogical device. I've invented. Yes, last night I don't want to go. Skilling is going to kill me if I start explaining all of these things. It's going to take like 3 days. So my pedagogical device is the diagonal line. The derivation exists. So the general sum rule. How about if you have propositions that are not mutually exclusive? Then actually one can write. We see that there is an additional term there, and we can prove it. And there's the proof. All right.
More explicit
Step 2. Then a miracle happens. Divine revelation is still my preferred method of proof. So there is a proof there.
Buy the book.
So now, how about the conjunction, the product rule? Now, remember, this is not Cox. It's not just two arguments, all right? Cox was using negation, right? So that's another kind of worms. Here we have this function that has 4 arguments. And so what we're going to do is, we're going to go step by step. Well, imagine it's the first 2. Imagine it's the first 3. We figure out all possibilities, and let's start with the easy one. So what I'm going to do is, and of course, the correct one we're going to see is number 3. The probability of A and B is the probability of A times the probability of B given A. So this is the one that's going to be correct. What I'm going to do is rule out all the others. And the way it works is that the results. G3, we're going to find out, if you go through the details, that it works, right? G1, G2, and G4 are ruled out trivially. And what I mean by that, and I'm not going to show it to you, but it's only 2 lines, is that if you actually believe that the rule for conjunction is G1, what you end up seeing is that the function G1 has to be uniform, constant, so that the degrees of belief of various propositions end up being 0.37, no matter what's going on out there, no matter what the proposition. So that's clearly ridiculous. So the requirement that those functions be non-trivial, non-constant, rules out those. Now, G5 had more than 2 arguments, had like 3 arguments. So of course, G5 is also equivalent to a theory with 2 arguments, provided it is independent of the third, right? So when you do the calculation properly, and I'm going to show that proof following my very quick pedagogical technique, G5 turns out to be equivalent either to G1, that doesn't work, or to G3, that is okay. G6, it's either equivalent to G3 or to G4, which is not okay. So this in principle they could be okay, but they're equivalent to G3. G7, it's either equivalent to G5 or G6, which are equivalent to G3. So all of these are saying, look, these functions are going to be okay, provided you only have 2 arguments independent of the third. So the proof of G5, here we go. We're going to use consistency. We want to eliminate irrationalities, and it's going to be the same problem, the same issue of this object here, the degree of belief of this and that can be computed in 2 different ways, and they ought to agree. And when you do that, you get a proof, and eventually, it's not even long, you see. It's not a problem. G6 and G7 are actually very analogous to that. So with this kind of argument, which essentially involves associativity constraints, what we have managed to do is that conclude that degrees of rational belief are assigned so that and is represented by a function g that depends on only 2 arguments. So what we have managed to accomplish here is essentially derive one of the axioms of Cox from somewhat slightly more fundamental considerations. By essentially showing, look, you could consider more general stuff, but it's not going to work. That's all. Now, to determine what G is, what I'm going to do here is something different from what Cox did. He used negation. We're not using negation here. What we're going to use is the fact that and or satisfies certain properties that come from your Boolean logic. So we're going to use, again, consistency, requiring that whatever G we have for AND, it should be compatible with the F that we had for OR, which was the sum rule. So what we're going to use here is distributivity. This is different from what Cox did. Right distributivity of B and C when B and C are mutually exclusive means the following. A and B or C is supposed to be A and B or A and C. And so if we apply the function G to this, we get a functional equation of this kind. This is way easier than the negation functional equations you get. In fact, this is so easy that I can actually do it without invoking my I can't do it. My pedagogical technique. But the idea is going to be very easy. How do you solve this functional equation for G? You notice that here we have V. That plus there comes from that or there. This comma comes from the and, right? So we notice here that we have V and V, W and W. If I differentiate with respect to V, I get a mess. But I kill the W. There is no V here. If I differentiate with respect to W, I get some mess here, but I kill that one. So if I differentiate with respect to both V and W, what I end up doing is killing the whole right side of the equation, and that makes things very easy. So what I'm going to do is call V plus W equals Z, differentiate with respect to V and W, and what I get is the second derivative of this guy here with respect to the second argument is 0. Now, second order differential equations like this can be solved even in a conference talk. If the second derivative is 0, the function is linear. Plug it back in to make sure, plug it in here to make sure it works, and you figure out that B is 0. So it's just linear, where there is a coefficient here that depends on the first argument. In order to figure out what this function here is, we notice that the degree of belief in A is the same, given D, is the same as the degree of belief in A, given D, A and D, given D, right? Because it's the same. The D there can be forgotten. In other words, use the G function for the conjunction, and you get something like that. The degree of belief in the first, the degree of belief here of the second, given the first. But this is true. So this is whatever number you use for the strength of your beliefs when you know that something is absolutely true. So this is the equation. A number, U, is a function of the same number and then a constant. But this function here, G, is linear. So we substitute back here. The second argument, V, is this. So now this tells us that AU is that U divided by a constant. I know this is difficult, and it's like doing algebra is something like you require privacy. Just do it. But anyway, I want to point out that it's only 2 lines. So now that we know what A is, we know that this function here is a product. Of course, it's a product rule, except for some normalization. So when we plug it back, what does the loose probability look like in this scheme? It looks like this, and there is this ugly normalization factor there. So if I divide both sides, we see that now the rule looks much more symmetric. We regraduate again, just a matter of convenience, and so then we obtain probability rule for the product, probability rule for the sum, where we can actually derive that probability is 1 or 0 for truth or falsity. Conclusion: degrees of rational belief have been designed. 10 minutes. Yes. Have been designed. This is good. This is good. Oops. No, we don't want more volume. I screamed loud enough already. Anyway, summary. Let me give you this is the end of the second part of the talk, and then I can start the third part of the talk. Probability theory. Please notice, this is crucial. It was a matter of design. The whole justification for the scheme is not that it is true. It's designed. It's because this is what we want to achieve, the kind of theory we want to build. This is nice. Okay, probability theory has been designed for reasoning with incomplete information. But the fact that I am using the words "I want to build a theory of this type" means that the chances that I'm going to be egregiously wrong are much smaller, because how can you claim that I don't want this? This is the theory I want to build. Now, if you want to build a different theory that is neither universal nor consistent, be my guest. You can do that. And for some purposes, it may be very valuable to build non-universal theories. It's fine, right? But here the justification for universality and consistency is mainly one of design specifications. The theory is not meant to be true. It is meant to be useful. Degrees of rational belief guide us as to what an ideally rational agent ought to believe, which flags interesting connections with ethics and all sorts of... When I want to really annoy people, I start saying that the foundations of science is ethics. And this can make them really squeamish. There is this whole idea in philosophy that the distinction between ought and is, it should be critical. Fact and value. No. Very well. Rationality may be difficult to define, but irrationality is much easier. At least instances of irrationality are very easy to figure out. And the design specifications are universality and consistency. Other theories are possible, but you may not find them as useful. Now, okay, so here. Let me start the third part of the talk, which presumably will take 5 minutes. And the purpose of the third part of the talk is just to essentially give an introduction to Adam's talk later. The issue is we have here some sort of scheme, a framework that allows you to get started on this business. What are you supposed to believe when you're confused? And at least avoid consistency. But this does not address the very important problem, the framework is not complete, of that there is considerable freedom as to how you assign these probabilities. So we need additional schemes that will guide us in the assignment of these probabilities. Now, once again, this opens up a completely new can of worms, which is, what is it that you want to achieve with one particular assignment over another? So, for example, the fact that there is considerable freedom in how you assign probabilities means that inevitably some subjectivity is going to sneak into the process, because you don't know enough. You may think that these probabilities or these instances are equally likely. You may think that. Well, someone else may think that they're not quite equally likely. You may assign different priors, and ultimately it's not easy to figure out how to do it. So some subjectivity is inevitable. Now, the crucial thing is that while subjectivity is inevitable, it is very clear that some assignments are objectively better than others. You can be objectively wrong. So, well, and they're going to be objectively better because somehow they are more useful. It is some beliefs are more useful than others. We could say that they lie closer to the truth. But this is a scary concept as well. What do you mean by true? Maybe something that it is useful to believe. Very pragmatic. So while it is true that subjectivity is inevitable, we want more objectivity. This is something that a theory that's completely subjective is not useful. Because if you're allowed to believe whatever you want, why would you ever want to change your mind? It takes an incredible amount of work to collect data. Why would you want to do that? So now, the theory is going to be useful. You want to recognize your subjectivity in order to control it, but then you have to strive for objectivity. So we need a procedure to improve probabilities. We have to recognize the inefficiency of having this, and recognize its inevitability and its inefficiency. And so we want a procedure to improve probabilities. So this brings us to the next problem. How do we update probabilities when new information becomes available? How do we do that? Interesting question is, what on earth is this word here? Is it green and goopy, and it attaches to propositions, and suddenly they're more informed? What on earth does it mean? Please notice that we may recognize that data contains information, but what is that? Okay, and so it is here that updating rules come in. Bayes' rule entropy. These are the updating rules, the ways we have to improve our probabilities. But then here's another question. What on earth is entropy? Why an entropy? Which entropy? These are all very legitimate questions to ask. And we have to be very clear what our design specifications are in order to have reliable answers to these questions. In particular, are Bayesian and entropic methods compatible? Is this updating rule compatible with that one? They better be. Of course they are. If you know what you're doing, if you know how to use, like James used to say, entropy is a very, very powerful tool. You can either use it to build beautiful furniture, or you can saw your thumb off. Right? Same thing here. There is lots of room for understanding how to use entropy in particular so as to make it completely consistent with the use of Bayes' rule. But that's not my talk. You see, you cut me off. Thank you.
I haven't cut you off, Ariel.
No, I know. It's just, I like it. We have this ongoing teasing here. Yeah.
What I think is wonderful is that 65 years after Cox, well into the next century, we're still developing, focusing, clarifying these ideas, and we're still not in full agreement, and this is great.
This is one of the few communities where we can disagree without getting really upset with each other. A little bit upset, yes, but really upset.
Just a short comment. I think the last statement you said that entropy is a powerful tool. The answer to that question depends on the answers to these questions first.
Yes. And I don't have time to talk about it. Adam probably will talk about it. Some of us believe. Yes. Yes.
Yes, a couple of questions. One you'll answer, the other one you won't be happy with. You said in your formulation there that these probabilities had to be real numbers, and my query is why real numbers? Why not an ordinal scale?
Or ordinal scale?
Ordinal scale, or for example, quotients. Why real and not quotients? So you're allowing the possibility of using irrational numbers for degrees of rational belief. This is just an interesting.
Oh, okay. The rational there doesn't have to be irrational. These are completely. Yeah. It's like imaginary numbers are not something that you imagine.
No, not right? I'm not talking about imaginary numbers. I'm just talking about irrational numbers like pi. Why would we have a probability of pi on 2?
I think that the whole idea comes down to what we're trying to do here is build a useful framework. If this framework happens to be useful and it performs its duty, it does what it's supposed to do, then it's good enough. Now, if you can come up with another framework in which the notions of differentiability or whatever are not needed, or whatever,
that would be the problem. Is that if you only have quotients, you don't have differentiability, and then you'd have to have
exactly. Now, the point is that it's not that this is the only way to do it. This is a solution that works in an engineering sort of approach. Now, and I mean engineering here in the best possible way. In other words, why would we want anything else if this is already working? All right? So it's part of the specifications. This is not the way it is because it is actually true, but rather because we want it to work and it's working.
Okay, as an engineer, I can accept that. Second question, I've always been very troubled by this consistency axiom, always, that you should be able to calculate things in different ways and get to the same result. Now, in real life, there's a cost associated with any process, and if you embark on one way of reaching some information, you will have a higher cost than others. And I've always wondered whether, and pity, I don't know if Kevin's here, but if we were to incorporate this cost, perhaps we'll end up with a completely different framework.
Yes and no. I understand that the cost is actually totally crucial, right? But I believe that what we're going for here is a framework that is designed to help us figure out a particular problem as handled by an ideally rational agent. So it is in this sense that the cost is part of the idealization we do not care about. Let me give you a different example, because of course, yes, these are questions that, these idiotic questions are really important, right? This is where we can actually go in a completely different direction. What I'm doing something is defining something like a calculus. If you want to think about the value of a particular integral, you may want to calculate that value numerically. Now, the calculus that we want to invent, that it is useful to invent, is one in which the actual area under the curve is a certain number, which may perhaps be unknown, but it is a very well-defined number. We would not want a calculus such that the value of an integral depends on what the state of the technology is, what is the chip that you're going to use to define the theory. So these are the practicalities that make all of this very idealized. So in the same sense that we would not want to have a calculus that depends on the numerical methods of approximation that you use, although that's very practically important, right? We do not want a theory of inference that will depend on how much money you have. Although maybe we have a point here, okay? Okay, politics works very much like that. Whatever is truth depends on the size of the country that's backing you up, right?
More of a technical question. When you did this regrading scale from this function of degrees of rational belief to these probabilities, on the right-hand side you had this thing in brackets, this degree of reasonable belief, and then on the left-hand side you had this function of two propositions.
Yes.
Is that like something trivial?
Okay. No, it's not a function of two propositions. It is a function of two numbers. Those numbers are the degrees of belief to the various propositions involved.
But when we actually use them, don't we say the probability of x given y, and we're free to change these propositions however we like?
Oh yes, that's why these functions are supposed to hold no matter if you change the probabilities or the propositions, these variables, x and y and u and v and all that, will change their values, right? So yes, it is, once you decide that these degrees of rational belief are numbers, the numbers are numbers until you can actually work with functions. So it's not a function of propositions, it's a function of the degrees of belief associated to those propositions, and you can actually change those variables at will. Sorry, I can't, we have to sit down and actually do it. Yeah.
So you have referred to such notions like usability, universality, pragmatism, usefulness. In all those cases, it seems for me that at the end of the day you refer to some notion of a posteriori epistemic verificability, which means that well, you choose the framework, or you say that the framework which is constructed by some rules is good or bad, not true or false, but good or bad, because you have some a posteriori pragmatic, well, epistemic verificability. So now my question is how you actually prove that this framework is epistemically verifiable, or more, okay, I know that many people have done calculations. I'm not asking as a person who is disbeliever in relative entropy. I'm asking as a believer who wants more. So the particular question is how you run from the problem of reference class of particular context when some particular methods are better verifiable than others, and well, it's this universality has particular restrictions, and I think that this should be made should be a topic of concern, or at least explicit statement.
I think if I understand you correctly, I think that the concern is very, very legitimate. And the way I would say that one can, I can't say bypass it. That's why this is pragmatic. Pragmatic approaches never give you something that's undeniably true. You never reach that sense of, this is inductive inference, for crying out loud, right? You can always be wrong. The way one would say one shows that this is actually useful is you build a theory based on this. So maybe statistical mechanics might be it, right? Quantum mechanics might be it. You build your theories, and to the extent that your theories continue to be good, you keep them. That's it. It's essentially the way societies do science. we are wrong, wrong, wrong. Oop, this works, let's keep it. Then it works, it works, it works. Then you say, oh, it's not working anymore. Let's fiddle around and change. What do you change? It's not working. What do you change? Do you give up on consistency? No, let's give on something else. Maybe I chose the wrong microstates. Maybe I chose the wrong constraints. Maybe I changed. But essentially, you never have this certainty that we seek. Certainty is not to be found in any of these methods. For certainty, you need religion. Here, yeah, sorry. Which is an approach. I mean, hey, it worked. It pragmatically worked, right, for centuries. So the method of divine revelation can be pragmatically very useful when you have the Spanish Inquisition breathing down your neck. So go ahead and do it. Anyway, so it's a serious problem, but the answer is no certainty is achievable, period. It's just utility, it's pragmatic.
Before we get into religion, I think...
oh, I like that. You know, the tutorials are meant to sort of raise the dust.
I'm so glad you ended your answer with some of those comments, because I want to ask you, what about transitivity? Is it sacred? In other words, if A is less than, if A is whatever you want, if A is something, B is something than C. Can you say a few words about that?
Okay, yes, I can. Remember, what we're trying to do here is build up a framework that's useful.
In other words, real numbers versus partially ordered sets, I think that's...
Oh, absolutely, okay. In certain circumstances, one may want to pursue something like this is strategy for thinking, but for example, if you're doing quantum mechanics, this is a very good example. If you're doing quantum mechanics, there is a sum and a product rule, right? So this is, how do we usually figure out these problems? You start from the answer and work your way back. It's not just students that do that, look at the answer at the end of the book, and then they cook up a solution, right? If we do the same thing. So you start quantum mechanics. Quantum mechanics has a sum and product rule for amplitudes. So many of us back in the 90s were, oh gosh, this is a sum and product rule. Where is Cox? Where is Cox? And so when you try to apply it properly, then you realize that complex numbers, there is no transitivity there. In quantum mechanics, there is no negation, right? So how do you actually handle quantum mechanics when there is a sum and product rule, but all the ingredients that Cox put in there are absent? So that's why in '98, that was the first time I came to these conferences, I came up with a scheme in which one could obtain sum and product rules for quantum mechanics by analyzing the particular ways in which you could put together experimental setups as if they were Lego pieces. You can put them in parallel, you can put them in series, you can do things like that. And so lo and behold, associativity works. There is distributivity. So this is how distributivity came into the picture. We couldn't use negation. And so that whole thing fell into place. But there was a very important lingering question. Since there was no transitivity, we knew that it couldn't. Well, it could be real numbers, but why? Maybe let's use complex numbers. So I didn't have a very good answer to the question, why should we use complex numbers? So let's use complex numbers and proceed. That is the kind of issue that was later addressed by Jean Skilling, Philip Goyal, and Kevin Knuth, saying, no, we can actually clean up the complex numbers business. It's not complete yet, I don't think, because then the issue is that if you're not going to use one real number, you have to use two. Then it's complex numbers, but why two? So these things remain, although.
I won't argue with that here. That's another question.
Yes. Yeah.
I wanted to ask, what is your opinion? Can this approach be treated in the future as true? For example, in my experience with is that after I construct a problem and solve it, and I experimentally test it, I learn something new. So if we gather many facts which confirm that it works, maybe one day it will be treated as true method, not only useful.
Okay, we're getting into a really interesting question, which is, what do we mean by true? Yeah. Will performing 10 experiments yield you truth? Or will it take 20? Or how many? Is it an infinite number? So the issue of truth is very important. And we should address it, because if we're talking about the degree to which you ought to believe that something is true, the next question is going to be, what do you mean by truth? Should we adopt a correspondence theory of truth? A proposition is true if it agrees, corresponds to some ultimate reality. Should we adopt that? Or should we adopt the pragmatic version of truth, which says, well, you'll say that something is true if you act according to it and it works and you keep surviving. Ultimately, it's Darwin. Darwin saves us all here. If you keep surviving, then it is true. Truth by virtue of being useful. The pragmatic approach to what truth is important. So I think that pragmatism solves these questions. Whether that's acceptable to scientists or not, I think, well, it's the next layer, next development.
I think we'll have a
the last slide, yeah. I like this. I want to join this, but then the next question is there any general agreement about usefulness? You talk about usefulness. Just comment.
It's a question.
Those are the good questions, right? You're an engineer. You ought to know. You want to build a bridge? If people can walk over it, good, right? And this is not any. Please notice that I'm a theoretical physicist, right? I'm trying to deal with the theories of physics in as fundamental a way as possible. And my conclusion in all of this is that physics is not more fundamental than engineering. Physics is not more fundamental than economics. Physics is not the most fundamental theory. Physics does not go after ultimate eternal truth. It's very lucky that I already have tenure, because if I didn't have tenure, I would never have, with these opinions, I wouldn't get it, right? This is it's a very heretical view of what we do when we do science. Yeah, so what's useful? I don't know. If you can make money out of it, maybe it's useful. Right?
One last question before that.
Okay, this is a question that maybe has a simple answer or maybe a complicated answer. That's how confused I am about this. And if it's a complicated answer, then since we have lunch afterwards, we'll discuss it over the week. On parts 1 and 2 of your talk, you're basically doing a very beautiful argument from consistency of how to build up probability theory. And if you look at De Finetti, he also has an argument of consistency. The language is different. He emphasizes bets. Here you emphasize functional equations. My question is, is there anything that would stop me from reformulating this argument in the language of De Finetti? Or is there something fundamental, and this has to do with the assumption of ideally rational that you bring in. I only see this coming in the third part of your talk, which you didn't give, where you talk about priors. If there's nothing fundamental about mapping these two proofs, that would be nice, because it means there's another reason for being friends with a subjective camp. Or if there's something fundamental, then that would be very interesting too.
I think that this comes under the heading of, if you want Bayesians to disagree, you only need two. Even two Definettians can disagree with each other about what they actually mean. There are some very personalistic Bayesians who actually believe that the probabilities reflect the degrees of personal belief of a particular agent, and you're going to talk to the person and figure out what it is that's going on in their mind. But what you're suggesting, and I think it's perfectly legitimate, right? You're suggesting is we could imagine an ideally rational Definettian agent who will actually behave just according to the appropriate gambling behavior that will lead to consistent or to eliminate certain losses, right? So if we rephrase it in that way, then I think that this ideally rational Definettian agent would probably fall under these other headings of degree of reasonable expectation or degree of rational belief. I think that we can make that. And it is to be expected that these things are done. If you sufficiently qualify these short descriptions of what probability are, if you sufficiently change them and say, oh, what we really mean is this, all of them eventually lead to probability theory. So maybe we can actually say, no, there is no disagreement. So my short answer would be something like this. It is possible to eliminate these disagreements with, or to formulate some of these ideas in terms of betting arguments, gambling, provided the fact that that it becomes clear that the personalistic judgments of individuals need not be equally legitimate, that there is some better ways to gain information, to update, you need to have that that fine print, okay? This is a complicated framework that comes with a manual with lots of fine print, and you have to be careful there.
I need to cut this short because we want food. There's one question which I'll allow to be asked if you can answer it in 1 minute.
I'm sorry, one last quick question, Ariel. Would you include in your list of what probability is? It's a generalization of logic?
That was the last one, degrees of implication. Right. It is a generalization of logic, yes.
Well,
yes,
then
yes.
I would say then certainty is achievable because certainty is achievable under logic and probability generalizes logic. So certainty is achievable as part of probability theory. I would agree with you on your statement that...
Okay, I think that certainty is achievable within a mathematical context, maybe. Even that is a little bit iffy. But when we're going to apply this, the idea is to apply this sort of theory to real problems. So there is, for example, the fact that you may want to say, I want to describe how a particular particle moves, and I can follow the laws of calculus and predict with certainty that it is going to be over here. But this is within this mathematical scheme. The certainty gets completely lost when you say particle. What are you talking about? Is this an electron? Does it diffract? Is there something bumping into it? Reality is way more complicated. So certainty is never achievable in this sense of making the scheme apply to real problems. In reality, that connection, that's why the correspondence theory of truth and the pragmatic theory of truth are an important distinction that we should study, which we have never in this conference.
On that note, I think we should move from the food of the mind to food of the body. First, congratulations.
Thank you.
Lovely talk, provocative, well in style of these conferences.